Before we learn the tricks for finding out the eigenvalues for some special matrices, let us just recap the conventional method. Now, if you have been given a matrix A, which is say 3 by 3, then the standard method of finding eigenvalues is finding the determinant of A minus lambda I and equating it to 0. When we do A minus lambda I and expand the determinant, we will get the equation looking like lambda cube plus A1 times lambda square plus B1 times lambda plus C1 is equal to 0, where A1 is the trace of matrix A with negative sign, B1 will be sum of the three principal 2 by 2 minors, and C1 is going to be opposite of determinant A. So let us take the example. In this matrix A minus 1 0 2 3 2 1 1 2, we have trace equal to 6, therefore A1 is minus 6. We have sum of principal minors, B1 is equal to 11, and then determinant of the given matrix is 6, therefore C1 is minus 6, and hence characteristic equation of this matrix is lambda cube minus 6 lambda square plus 11 lambda minus 6 is equal to 0, which gets factorized into lambda minus 1, lambda minus 2, lambda minus 3 is equal to 0, and hence the three eigenvalues of this matrix are 1, 2 and 3. So corresponding eigenvectors we can find out, and we get first eigenvector as minus 1 0 1, second eigenvector as minus 2 2 1, and third eigenvector as minus 1 2 1. So you can just go through this procedure. This is a standard procedure of finding out eigenvalues and eigenvectors, and if you can practice for 3 by 3 matrix, it is more than sufficient. But these calculations are going to be long, sometimes very difficult also, and therefore we must know some tricks for finding out the eigenvalues of a given matrix, say 3 by 3, very quickly. And if that matrix is a special matrix, then there are some tricks by which you can get eigenvalues and sometimes eigenvectors also very quickly. Therefore, in this video we will learn a few more tricks to find out eigenvalues very quickly and maybe corresponding eigenvectors. Let us look at trick number 1. For example, we have a matrix 4 0 0 0 minus 2 0 0 0 7, and the matrix is such that it has got the entries at principal diagonal, everything else is 0. So this is your diagonal matrix, and in this case the eigenvalues are straightforward. First eigenvalue is 4, second is minus 2, and third is 7, because all other things are 0, and therefore first eigenvector will be 1 0 0. So if you orally try to check multiplication of 1 0 0 with the given matrix, you will get 4 0 0, which is 4 times 1 0 0. If you take second value, eigenvalue is minus 2, and the vector is going to be 0 1 0. So first column 0 times, second column 1 times, and third column 0 times if we take, then in RHS we will get 0 minus 2 0, which is minus 2 times 0 1 0. So minus 2 is eigenvalue and 0 1 0 is eigenvector. Same will be the story for eigenvalue 7. If you take first vector 0 times, second vector 0 times, and the third vector 1 time, then you will get 0 0 7 as your RHS vector, which is 7 times 0 0 1. So if you happen to have a diagonal matrix, the entries in the diagonal, principal diagonal, are the eigenvalues. But this is simple. Let us look at trick number 2. Now suppose the matrix is looking like this: 2 0 5 9 10 7 8 0 3. Then only in column 2 we have 10 at correct position: 0 10 0. So second vector is at correct position, and therefore the lambda, which is eigenvalue, one of the three eigenvalues of this matrix A, is going to be 10, and the corresponding eigenvector is going to be 0 1 0. Now you can get information about the remaining two eigenvalues because the trace is 15, out of which we have got one eigenvalue equal to 10. So sum of the remaining two eigenvalues is going to be 5. And if you evaluate this determinant, then the determinant value divided by 10 is going to be the product of remaining two eigenvalues. This is the information that we get out of this. Let us look at trick number 3. Now trick number 3, consider the matrix looking like 2 3 8 12 13 14 0 0 7. Now what is so special about this matrix? 0 0 7, the third row, is special. We note that the eigenvalues of a matrix and the eigenvalue of transpose of that matrix, they remain same. The eigenvectors are different, but the eigenvalues are same, and therefore even if we have row 0 0 7, the transpose of A will make that 7 in correct position, and hence the eigenvalue of this matrix A, the first eigenvalue you can consider of this matrix A, is 7, and then again the remaining two eigenvalues need to be found out, but the information about the trace and the product of remaining two eigenvalues can be easily available. Solving quadratic is easy compared to solving cubic. Therefore, by looking at the matrix, if we can easily get even if one eigenvalue very quickly, then the job becomes very easy. Now let us look at trick number 4. Consider matrix 5 2 2 6 2 1 7 3 minus 1. Now what is so special about this matrix? You will find that this matrix, every row adds up to 9. So you can consider the first eigenvalue to be equal to 9. Why? Because if we take first column 1 times plus second column 1 times plus third column 1 times, we will get the RHS vector equal to 999, which is 9 times 111, and therefore eigenvector corresponding to eigenvalue 9 is 111. This is interesting. If you get the summation of the rows of the matrix equal, all the three rows have summation equal to 9, then directly you can say one of the eigenvalue is 9 and corresponding eigenvector is 111. So this is a good trick to know. You can find out the trace and determinant to find out the remaining two eigenvalues. Now the trace in this case is 6, and therefore lambda 2 plus lambda 3 is equal to minus 3, and determinant of the above matrix is 9, therefore lambda 2 into lambda 3 is equal to 1. Therefore the quadratic which we have to solve for getting lambda 2 and lambda 3 is lambda square plus 3 lambda plus 1 is equal to 0. So by inspection we could find out first eigenvalue, corresponding eigenvector, and by solving quadratic we will be able to get the second and third eigenvalue, and we will have to find out the second and third eigenvector correspondingly. Now let us look at the next trick, trick number 5. Consider a matrix 3 5 6 2 2 3 2 0 minus 2. Now what is so special about this matrix? That all the columns add up to 7. So same story, if all the rows add up to the same number or all the columns add up to same number. The first eigenvalue is the value of that summation. In this case, lambda 1 is equal to 7, and similar to the earlier matrix, we can find out remaining eigenvalues and corresponding eigenvectors. In this case, for lambda 1 is equal to 7, you will have to follow the procedure to find out the eigenvector. Let us now look at trick number 6. Let us consider the matrix 1 to 10, 2, 4, 20, 3, 6, 30. What we observe in this matrix is first column, if we multiply by 2, we get the second column. So first two columns, they are not two linearly independent vectors. Second vector is dependent on first, or first is dependent on second. But the third vector is different. Therefore, in this kind of matrix, we can directly arrive at one value of lambda, which is eigenvalue, which is equal to 0. That is essentially because all the three vectors are not linearly independent. And if you go through the lecture note, you will understand why is this going to be 0. But let us right now focus on the trick. If you have two columns or two rows which are linearly dependent, then one eigenvalue is 0. So corresponding to eigenvalue 0, the eigenvector is also easy to find. Basically, if we take first column 2 times and second column minus 1 times, that means they add up to 0, then the eigenvector is 2 minus 1 0. Eventually, when you multiply a by 2 minus 1 0, you will get 0 0 0. So the eigenvector also can be easily found out in this case, and the first value is 0. Therefore, the cubic in lambda will not have a constant term. C1 is going to be 0, which is determinant. Because the two columns are same, the determinant is going to be 0, and hence finding the quadratic equation for the remaining two eigenvalues is going to be easy. I have done some calculations to find out the quadratic equation, which comes out to be equal to lambda square minus 15 lambda minus 100 is equal to 0. So lambda 2 is 20 and lambda 3 is 5. Again, all these three values are distinct. Because the first value is 0, we can find out the remaining two values very quickly. We can check the trace also. It is 15, so 20 minus 5 is equal to 15. Let us look at trick number 7. Let us take the example where we have a matrix. All the three columns are linearly dependent. So the third column also, now the last entry was 10 earlier, now I made it to 30. So first column, if you take first, then second column is twice multiple of first column, and third column is 10 times multiple of first column. So every column is a multiple of 1, 2, 3. Therefore, in this particular case, the matrix has got two eigenvalues which are 0 and 0, equal to 0. So in this case, lambda 1 is equal to 0 and lambda 2 is also equal to 0. Now we can have two linearly independent eigenvectors for the value 0. Suppose we take 2 minus 1 0, which is our trick number 6 eigenvector for first 0. Then we should avoid taking first two columns, and we should take either second and third column or first and third column. So if we take first column 10 times and 0 times second column and minus 1 times third column, then the summation is going to be 0 0 0. The eigenvector is 10. 0 minus 1 will give us in right hand side 0 0 0. Therefore, two linearly independent eigenvectors for the same eigenvalue, which is 0, but repeat two times. Therefore, two linearly independent eigenvectors we could write. I mean, you can represent these two eigenvectors differently. This is one of the examples that I have given. Now, the trace of A is 35 and two eigenvalues are 0, 0. Therefore, of course, the third eigenvalue is going to be 35. Now, for finding out the eigenvector for the value 35, it is again going to be simple. Look at this. If we take first column one time, second column two times, and the third column three times, we get total. First row becomes 35, second row will become 70, and third row will become 105. So, if we multiply 1, 2, 3, which is eigenvector with matrix A, we will get 35, 70, 105, which is 35 times 1, 2, 3. So, eigenvector in this case, third eigenvector in this case is 1, 2, and 3. Very interesting. Let us look at trick number 8. Let us take the example where we can observe something special in this. Now, in this matrix A, you will find that 7 is in correct position. Therefore, first eigen value is 7. Then all rows add up to 10. Therefore, the second eigenvalue is 10. So now we are having two eigenvalues with us. For 7, the eigenvector is easy, 0, 0, 1. For eigenvalue 10, again the eigenvector is easy, 1, 1, 1. And now if we look at the trace, already we have got two eigenvalues with us. Therefore, finding the third eigenvalue is going to be absolutely easy. So, trace is 14 and therefore third eigenvalue is minus 3. Now, you will have to do the work for getting the eigenvector for minus 3, and we know the procedure. I mean, we just find out A minus 3i times our vector is equal to 0. So, what should be that vector? Non-trivial vector which makes the right hand side 0, and finding out the eigenvector in that method. In this case, in this particular matrix case, we have got third eigenvalue equal to minus 3, and the eigenvector comes out to be 40 minus 25 and 1. So this is also an interesting example. Let us look at trick number 9. This 0, 0, 1, 0, 4, 0, 9, 0, 0. Now, in a trick 1, we have seen a matrix where it was a diagonal matrix, all the entries on the principal diagonal. Now, this is all the entries where it is not principal diagonal. So, 0, 0, 1, 0, 4, 0, 9, 0, 0 is the special case. Column 2, you will observe the 4 is in correct position. Therefore, one eigenvalue is 4 and corresponding vector is 0, 1, 0. Then the trace is 4 and the determinant is minus 36. Therefore, you will find that the characteristic equation is lambda square minus 9 is equal to 0. Therefore, lambda 2 and lambda 3 are 3 and minus 3 respectively. We need to find out the eigenvectors, and you will observe that that job is also easy. When we consider 1 times first column and 3 times last column, we get the corresponding entries 309, which is 3 times 103 in case of lambda 2 is equal to 3. And if we take first column as 1 and last column as minus 3, then we get resultant vector minus 3, 0 plus 9, which is minus 3 times 1, 0 minus 3, and hence you get the eigenvectors also very quickly. So it doesn't matter whether your principal diagonal you have all the 3 entries or the other diagonal if you have all the 3 entries. Finding out eigenvalues is anyway relatively simple, and eigenvectors are also relatively simple. Okay, this is the last trick where we are considering 5 by 5 matrix A. The only thing is the submatrix 3 by 3 submatrix and 2 by 2 submatrix, they are simple and already considered in our earlier tricks, and therefore it is interesting to find out all the eigenvalues of these 5 by 5 matrix. Now for the first, because remaining last two rows are 0, first three entries are 0, therefore the eigenvalue for the 3 by 3 matrix are going to be lambda 1 is equal to lambda 2 is equal to 0, and lambda 3 is also going to be equal to 35, and therefore corresponding eigenvectors will be 2 minus 1 0 0 0, 10 0 minus 1, and 1 2 3 0 0, which we have already found out. Now as far as the 2 by 2 small matrix is concerned, lambda 4 we can find out because the sum of rows equal 3, therefore lambda 4 is equal to 3, and you can take fourth column 1 times and fifth column 1 times and add them, we will get 0 0 0 3 3, which is 3 times 0 0 0 1 1, and hence lambda 4 is equal to 3 is the fourth eigenvalue, and corresponding eigenvector is 0 0 0 1 1. Now the remaining eigenvalue is trace. We already know trace, and we already know 4 eigenvalues, therefore the last eigenvalue using that method is minus 1, and for minus 1 we can again orally find out the eigenvector 1 times column number 4 and minus 1 times column number 5 will give you the corresponding eigenvector. So this is trick number 10, where we consider 5 by 5 is going to be very difficult matrix, but if it is special and if we can observe the speciality of that matrix, then we can find all the 5 eigenvalues and corresponding eigenvectors very quickly. I hope these 10 different tricks are not very difficult to remember. Once understood, they will remain with you. Therefore, you can observe the given matrix first. If there is something special, then some of the eigenvalues are already available, and then you can work on remaining eigenvalues and eigenvectors very, very efficiently if it comes to finding out eigenvalues and eigenvectors in the exam. Hope you have understood this particular video and you have enjoyed it. I request you to keep visiting my channel, subscribe it, tell your friends to go through these small videos so that concepts become clear and your speed and accuracy during calculation improves. Thank you.